designed by processes that were made for a different era, were made for a different world, a world of certainty.
Be comfortable with the fact that you don't know, no one's going to know everything, and if this is still something that's scary or something that's new, that's okay, and that's normal.
So a mechanic can look at the car and analyse what's wrong with the car. You can look at your code and go, I'm expecting this outcome, and so I can close that gap.
I think it's probably safe to say that open source won the battle of how software is developed.
Und was wir jetzt tun müssen eigentlich als IT ist, wir müssen es schaffen, nicht unsere eigenen Prozesse zu optimieren, sondern wir müssen die wahrgenommene Geschwindigkeit optimieren.
Thanks for coming and welcome to JAX DevOps 2019. My name is Sebastian Mein, and I'd like to welcome all of you on behalf of SNS Media, the company organizing this conference as well as many other conferences. The history of the brand is a little bit interesting because we are, especially here in London, known as makers of the JAX conference, the JAX London conference. It used to be several times also in this building, and normally it's in fall in another building here in London. And we just said, okay, because in JAX conference is about application development and it's about the Java platform and software architecture. And we said, okay, we want really to extend the focus more towards DevOps. That means more towards modern infrastructure, more towards operations, of course. And so sometimes it's a little irritating because this conference is not about Java, but it's kind of in the spirit of looking at the latest technologies and really being kind of looking to the agile approach of things. Yeah. So this is a conference about DevOps, and I'll show you later the tracks which we used to organize the program. You'll see at every time 3 sessions in parallel to choose. They are in this room, they are here in the next room, and they are downstairs in another room. Yeah. So I'm pretty sure that you find lots of stuff to watch and to listen for you. These days, you can find on the web many articles about 10 years of DevOps. It's not crystal clear when it all started because, as many things, it was kind of a perfect storm moment. Lots of people were thinking how to change things, how to rethink things. But one can say that it kind of started with 2 presentations. One was in 2008 by Patrick Dubois, who also started the DevOps Days of movement. This was in 2008 about agile infrastructure and operations. And then Andrew Schaffer and Paul Nazareth did in 2009, independently from each other, also a presentation on agile infrastructure. The idea really was, okay, after some years, after the Agile Manifesto has been published and with a specific focus to software development, yeah, they said, well, why don't we apply all those principles and ideas and values and everything what is written there to the idea of operations and the idea of infrastructure. So these things happened at that time, and 2010 also another very important book appeared, Continuous Delivery, written by our keynote speaker, which I'm going to announce in a minute, and Jess Humble. And also this book, Continuous Delivery, is also about, let's say, the idea of obsessive automation, so the idea of the transition between development and production. So the entire DevOps movement, as you all know probably, there's not a crystal clear definition because this is good. I think it's really interesting that to see this is a movement consisting of many different, let's say, topics which several peoples are pushing forward. It's the idea really of bringing Agile not only to the software development process, not only to operations, but the idea of bringing the Agile mindsets to entire organizations. And I said it's really the idea of focusing on automating as much as possible. And last but not least, of course, using ultra-modern infrastructure, mostly cloud, containers, Kubernetes, and all that things, to really support that mindset. We collected here more than 30 sessions, keynotes, workshops. Some of you already went to the workshop which have been started yesterday on the pre-conference day. More than 30 speakers are here. And last but not least, a pretty international audience. And again, I'm really looking forward to the next 2 days because it's going to be an exciting gathering here with lots of inspiration, hopefully, with lots of exchange and lots of good ideas, which really help you to push stuff forward inside your organization or with your customer. The conference tracks, as I already mentioned, you find them structured in those categories. It's about continuous delivery, Docker Kubernetes world, microservices, cloud platforms, agile business culture, And last but not least, monitoring diagnostics, so really using data to understand what's going on. To have a nice overview, please use our mobile app, which we are offering. It's available for Android and iOS. You find it under the title JAX London Conference, yeah? Because again, this is a kind of the sister conference of our JAX London Conference. Just search for JAX London Conference and you receive the conference app for this conference. It helps you on the one hand to check the program and to mark your favorites, yeah? And secondly, it's also very important not only for us as organizers, but also for all the more than 30 speakers, as I said, to give you feedback. And as we all know, feedback is super important, feedback is crucial. All of us really want to learn what we can do better for the next iteration. So please give a feedback. Please be honest, please be fair, but really give a direct and honest feedback. It is really appreciated, again, from our side as organizers as well as from the speakers' side. Having said that, I'd like just to hand over to our very first keynote. I just said Dave is one of the two authors of the book Continuous Delivery, which really has a huge impact on the way we think about the transition between product development and production. And so it really, the concepts have really brought an essential part to the DevOps mindset, I would say. And yeah, Dave is a software consultant, a thinker, a conference speaker, a book writer, and I would just like to say, give him a hand and welcome Dave Farley.
Thank you.
Welcome.
Thank you. Morning, everybody. Cool. Good. You can even see the slides, but bonus. Welcome, everybody. So I started the early part of my career often with job titles like software engineer, junior software engineer, senior software engineer, that kind of thing. And then didn't really like the term engineering. They thought it was wrong. They started talking about software craftsmanship, and this was much more like a craft than it was like an engineering discipline. And I agreed with them, and I had jobs like software developer or whatever else instead. And then in the latter part of my career, I started working in some very technically challenging areas and started doing things that felt a little bit more like they might be engineering. And that started me thinking, that and continuously working on continuous delivery and developing that approach to software development started me thinking about, what is an engineering discipline? What should an engineering discipline be? And that's really what I want to talk about this morning. So I want to talk a little bit about what software engineering is and what maybe it should be. I think for many of us, if you mention the term software engineering, it conjures up a picture like this. And this is to software engineering what a soldering iron is to electrical engineering. It's not the same thing. This is just a tool. It may be a good tool, it may be a bad tool, depending on what you're doing, but it's only a tool. This is not engineering. This does not define what engineering is. I think the other way in which we sometimes think about it in our discipline, partly because we've got this kind of thing wrong very often, is that we think in terms about the development process and the kind of culture in which development happens, and we think about stuff like this. This is a picture of the Scrum process. Anybody, any idea how many times the documentation for Scrum mentions the words code or software? I will tell you, none. It doesn't talk about code or software. Scrum is a good process, a good approach for managing projects, but it's equally good at managing plumbing projects as managing software projects. It says nothing about software or software development or software engineering. And so this too doesn't really cut it in terms of defining what we mean when we think about engineering in these terms. As I mentioned, at some point in the industry, the idea of software craftsmanship became popular. And craftsmanship is an interesting idea. I think there are some good reasons why the idea of craftsmanship took off, and I'll describe those in a little bit more detail in a couple of minutes. I think there's some good reasons why that happened, but nevertheless, craftsmanship is not the same as engineering. It's not the same thing. It doesn't. It may be a precursor. It may be related, but it's not sufficient on its own. And I'm going to talk about that in more detail as well. I think one of the ways of thinking about this and starting walking into this as a problem is to think about the history of human production of things. And I think broadly you can divide that up into 3 different phases. The vast majority of human experience, the vast majority of us making things was craft-based. For tens of thousands, possibly hundreds of thousands of years, everything that we created was the artifact of a craft-based process. And that had some pluses and minuses. Around about the middle of the 19th century, as the sort of Industrial Revolution had sort of took hold, mass production became more of a thing. And that improved the repeatability and the quality of the process, because one of the downsides of craft is it tends to be a bit low quality, a bit variable in quality. And then at the end of the Second World War, they started applying a little bit more kind of scientific rationalism to the idea of processes and production engineering, and they started using lean production techniques. So let's talk a little bit about each of those. So craft-based production, I think that we tend to have a fond regard for craft-based production techniques. I think when we think about it, if we are very wealthy, we kind of like hand-stitched leather in the seats of our cars, and we like to have these unique artifacts that were built by some expert and that kind of stuff. But if you think about it, in reality, craft-produced artifacts are actually low quality. Just for a moment, imagine a craftsman built one of these. It's a ridiculous idea. Even the prototype for this thing needed sophisticated engineering and working to tolerances that go way beyond what any human being can do by hand. Craft-based production it has some important aspects. It's the creativity involved with it is important, but the quality and repeatability of that kind of process is poor. We can't do things at a high level of tolerance. As a species, we are now at the stage where we can manipulate individual atoms. We can manipulate subatomic particles. Human beings can't do that with any tools. You need engineering-style thinking to be able to do that kind of thing. The next step up is mass production. And as I said, mass production, often when we think of mass production, we think of Henry Ford building cars. The first real example of mass production was actually a little bit more unfortunate than that. It was making weapons. It was making arms for the American Civil War. One of the horrors of the American Civil War was that it was the first real, truly mechanized war. And so they were able to kill people at a much higher rate because they mechanized the process of building weapons. But there's an amusing story, if you can have an amusing story about something as tragic as a war, but there's an amusing story about the man who wanted the contract to make the rifles for the northern states in the American Civil War. And he went into Congress with a sack full of rifle components. And he tipped the sack out on the floor of Congress and asked the congressman to select different pieces from the pile of components, from which he assembled a rifle. That was the first time in human history where you could do that. That was the first time where component standardization, the accuracy of the engineering, was sufficient to allow you to build things in that kind of way. And he won the contract as a result. So mass production kind of brings in ideas like assembly line, standardization of components, standard steps to make things, and all that kind of stuff. And that kind of took hold. That became the driving way in which human beings made stuff for nearly a century, well, maybe slightly over a century. And then lean production came in at the end of the Second World War. Deming went to Japan after the Second World War, and part of Japanese culture, there was sort of the Toyota process of building things kind of aligned with this nicely and with his ideas nicely. Essentially what Deming did was he applied the scientific method to production engineering and to process design. And so he invented this kind of approach to, he gave birth to this approach that ended up being what we would now call lean production techniques. If you look at any modern factory making almost anything these days, it's going to be using lean production techniques because they just work better. If you want to waste an afternoon, go and search YouTube for lean and paper aeroplanes, and you will see lean ideas described and exemplified by people making paper aeroplanes in kind of amusing ways. But it just works. It is mathematically, it's a more effective way of making stuff. There's another way of thinking about this, and one of the organizations, the group of people that are good at process and thinking about processes are chemical engineers. As you might expect, it's kind of their job to kind of formalize and productionize processes to make different kinds of stuff. And they have a taxonomy for different process control methodologies. So here's a description of one of them. This is the defined process model. The defined process control model requires that every piece of work be completely understood, given a well-defined set of inputs, the same outputs are generated every time. A defined process can be started and allowed to run until completion with the same results every time. Anybody think that sounds like software development? Me neither. This is the natural home for mass production, assembly lines, and waterfall processes. Waterfall processes work wonderfully if you've got a defined series of steps that are repeatable, but it bears no relationship whatsoever to the problems of software development. Here's another process model. So this is the empirical model of process control, provides and exercises control through frequent inspection and adaptation for processes that are imperfectly defined and generate unpredictable and unrepeatable outputs. I don't know about you, but that sounds an awful lot more like what we do for a living. We are always exploring and trying to grow our understanding of a problem. This is the natural home for craft-based production. I think this is one of the reasons why software craftsmanship became a thing. It was kind of in reaction to the kind of mass production mistakes that we made with software development process through the 80s and 90s, where we tried to apply assembly lines in effect to software development. And so in reaction to that, we kind of made this move and we switched to kind of craft-based thinking. But as we said, the quality is variable. It tends to go up and down. It's about exploration. It's about continual improvement. And it's the home of lean process. So where are we as an industry? I think we are not and never will be and never should be a mass production kind of problem. One of the clues is in the name. Mass production is about producing things. We don't really have a production problem. Our problem is one of design. Our problem is a problem of discovery, of learning. And we should be optimizing to be able to be really, really good at learning and design and exploring ideas, not producing things. If we get this right, if we automate everything, production is just pressing a button and cloning whatever it was that you had before. Production for us is essentially free, and so that's not our problem. So mass production is not the right answer. I think where we are is a craft-based industry, and you can kind of see that in the variability in different organizations. I make a living these days as a consultant. I go around and I advise companies all over the world about how to improve their software engineering or software development processes. And I see huge variance in the ways in which people work and the quality of their work. There are massive differences between the people that are doing really well and the people that are not. I think that where we should be shooting for is something closer to kind of lean production techniques, but we're not there yet, and so I think we should be moving in that kind of direction. When we start applying this kind of thinking, the impact on the outcomes is dramatic. We are not talking about 5 or 10% improvements in quality, productivity, the pleasure that our users take with using our software and so on. We're often talking about numbers that are closer to orders of magnitude changes. When HP first started applying the ideas of continuous delivery, which I think aligns with some of the stuff that I'm talking about, they saw an 8-fold increase, 8 times increase in productivity of their software development teams. They were a bit pathological when they started, so there was a lot of dead wood to remove. But nevertheless, that's the kind of improvement that we're talking about. And this has a serious economic impact. This has a bottom line impact on the organizations in which we work. Organizations that practice the kind of disciplines that I'm talking about make more money than organizations that don't. That's significant, that's important. I've been talking about this kind of stuff. I've been talking kind of around the edges of software engineering now for quite some time. And so I get involved in quite a lot of conversations talking about engineering. And as a side effect of that, I get involved in a surprisingly large percentage of organized conversations about bridges. What often happens to me is people say, yes, but software development is not bridge building, is it? So, well, no, it's not. But then, bridge building probably isn't what we think bridge building is. As an industry, I think one of our unique talents is misunderstanding what other people do for a living and probably belittling it sometimes. Bridge building is different. If you're building the first kind of bridge ever, that's a very, very different kind of experience to building the 3,000th suspension bridge made of concrete and steel. If you're building the 3,000th bridge, there's books written about how to do that. There's probably a program that you can do. You type in how long it is and it tells you how much concrete to order, I don't know. But it's going to be simpler than designing a new kind of bridge. If we decided that we were going to build a bridge out of carbon fiber that went from here to France, that would be a very, very different kind of thing. We'd be doing sort of research and investigation and discovery. That would be a design problem, not a production problem. And I want to kind of reinforce that point because we get hung up with that idea too much. Our problem is not a production problem, our problem is a design problem, and that's the kind of engineering that I'm talking about. How do you apply engineering thinking to design problems? So bridge building is software development engineering is not going to be like bridge building, but then bridge building isn't like house building. They're different. It's not like aerospace engineering, it's not like chemical engineering, it's not like electrical engineering, it's not like space system engineering. All of these engineering disciplines have their own unique approaches and attributes. But there are some similarities that we could kind of that we could use to identify what engineering really means. So engineering is certainly different. So one thing that we can know for sure is that if we wanted to define something that was software engineering for us, it's going to be different to anybody else's definition of engineering. It's going to be ours. It's going to be our thing. There's another way in which engineering is not the same, and that's in terms of scale. When we're talking about physical things like buildings, this is kind of obvious. These two structures are engineered structures. You can bet if this was an IKEA shed, they would have engineered it to the last degree to make sure that they're using the minimum amount of wood and then it was working to a price point and it was stressed just right and all that kind of stuff. But nevertheless, the level of engineering that goes into building a shed is going to be, it's obvious that it's a completely different scale to the engineering that goes into building something the world's tallest building. For this, people will have been building models in computers. They'll have been probably building physical models. They'll probably been putting them on shake tables to simulate earthquakes. They'll have put them in wind tunnels to simulate wind effects. They'll have been taking measurements. They'll have been measuring the materials and the stresses in the materials. They've been doing all sorts of things to discover how that worked. For software, it's not quite so evident sometimes. Is it, to the man in the street, the person in the street, is it evident that the engineering that goes into building, I don't know, an aircraft control system should be different to the engineering that goes into writing software for my mum's cake shop? I think they should be. They should probably be a little bit more diligent if people's lives are at risk. But it's not evident that what the differences should be to most of us. And actually, there's nothing to stop me going and applying without the relevant qualifications and getting a job writing software for a nuclear power plant. I could do that. And is that a good thing or is it a bad thing? It's a thing. It's a facet of our industry. So engineering is not the same. It's not the same in terms of nature, and it's not the same in terms of scale. So let's start digging in and thinking about what engineering really means. And as I said, I've been talking about this for a little while, and so I tend to get involved in these conversations. I got this tweet a couple of years ago from somebody, and I've blanked out their name because I just disagree with the tweet so strongly. So this person said, for me, engineering means working in a certified, inflexible process that includes planning ahead a lot, the antithesis of agile. I'm afraid I think that's nonsense. I think that's mistaking the production engineering with design engineering. If you're building the Curiosity rover, do you think it's an inflexible process that is involved planning ahead a lot? No, it's going to be about discovery. It's about trying stuff out and finding things that don't work as much as it is finding things that do work. So I don't think that's correct. Here's a definition from Wikipedia. So this kind of gives us a starting point. And there's some words that tend to crop up in these definitions and repeat. It's about empirical evidence, scientific knowledge, practical knowledge, and it's about tools and systems and components and processes and organizations. So it covers quite a lot of territory. Here's another definition, and this is about the science of making practical applications. The same kind of words are cropping up again. Again, yet another definition, scientific and mathematical principles to practical ends, efficient and economical structures. So this is my working definition. So for the rest of this presentation, when I use the phrase engineering or software engineering, this is what's in the back of my mind. Engineering is the application of an empirical scientific approach to finding efficient solutions to practical problems. And I think all of those words are kind of, I think it's a reasonably good definition. It's concise. I don't think you can take any of the words away without breaking the meaning. And in terms of efficiency, I mean both economically efficiency as well as efficiency in terms of performance and productivity. I think that there are some principles that we could agree. So I again, in one of these sort of Twitter conversations I got involved in, I was speaking to somebody and the person came up with this great idea. He said that if you were to come up with something like software engineering, it should be as true in 100 years' time as it is today. And I thought, he's absolutely correct, because the principles should be the same. So if we were looking to, I think one of the mistakes that we've made in the past in thinking about software engineering is to not think about those fundamentals. We've tried to do things like say, oh, software engineering is my favorite language, my favorite technology, my favorite diagramming system, or whatever else it is. And I don't think that's right. So one of the things that's probably true of something that we would call software engineering is we'd probably already know quite a lot about it, and we probably already largely agree on some of those principles. So these are my 5 principles that I think are a reasonable starting point. I don't think this is all that there is to it. I think there's some other things, but I think these are kind of foundational. The first is that I can't conceive of anything that we could credibly talk about as engineering that wasn't iterative. I can't imagine not concretely and aiming to get effective, valuable feedback as part of the approach. I can't think of doing this in an incremental way. We build complex systems by first building simple systems and adding and adding and adding. So incrementalism is important. And one of my hobby addictions is reading about physics, so I can't believe anything that we do in this act of discovery is not going to be based on empirical discovery and experimental thinking, trying out ideas, evaluating them, measuring them, and understanding their impact. So these seem like foundational ideas. So let's go into those in a bit more detail. So iteration is the act of repeating a process, blah, 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 blah. The interesting bit is with an aim of approaching a desired goal, target, or result. So we want to iterate towards some kind of result that we have in mind. Iteration is really important because it allows us to learn, it allows us to react to what we learn, and it allows us to adapt to what we've learned. I would say that iteration is one of the kind of key steps behind agile thinking. The idea of inspect and adapt is kind of fundamental to any kind of agile discipline, any kind of agile thinking. And that's just about the application of an iterative approach to learning, to continually learning and growing our understanding. Iteration allows us to steer towards a goal. If we decided that we wanted to drive from here to Edinburgh, we don't kind of plot a route and set a compass course and say Edinburgh is about 4 degrees from here or whatever else it is and just head off in that direction. We have a rough idea of where we're going to go, and then we're going to maybe listening to traffic reports or looking up to traffic on Google, or maybe there's a road, an accident or something like that. We're going to change our route. We're going to replan. Iteration allows us to do that by continually reflecting on what it is that we observe and what it is that we understand. It allows us to adapt and move forward. It also allows us to improve the things that we do. Our first attempt at something is always going to be worse than our 10th attempt at something. And so through iterating around ideas, we can improve them. We can make them better and better and better. And lastly, this is kind of related to that first one, it also allows us to train ourselves to become better and better and better. If you release your software once every 6 months, you're not going to be very good at it, to be honest, because you're not releasing it frequently enough to address the problems. If you're releasing your software every 11.6 seconds, like Amazon do, you're going to be really good at it because you've forced yourself to be good at it. And so it allows you to train and enhance your skills and experience. Feedback. Feedback is information about actions to return to the source of the actions. The way that I think about continuous delivery is that it is a feedback mechanism. It is fundamentally about applying feedback. And that was kind of in my head when I was doing work on trying to improve our software development processes. Feedback is vital. It allows us to reflect on what it is, on our choices, and improve in future. It allows us to distinguish between good ideas and bad ideas. This is the kind of schematic that I tend to use for when I'm talking about continuous delivery. At the outside, we have the kind of main feedback loop, have an idea, get useful software into the hands of users and figure out what they make of it. At the inside, we've kind of got the fast loop of test-driven development, and in between, we have other kinds of validations. But I would argue that whether you apply this approach or not, feedback is absolutely front and center in any quality approach to software development. I can't imagine being able to do that without high quality, fast, short cycle feedback. That's the way that we do good work. We want to work incrementally. Evolutionary design, continuous design, evolutive design, or incremental design is directly related to any modular design. My wife tells me that I'm a serial nerd, but she's wrong because I'm a parallel nerd. I'm a nerd on multiple fronts at the same time. And one of my nerdisms is aviation and the space program. So I want to tell you, I'm going to use a little bit of space rocketry because the pictures are cool to talk about modular systems. This is the Saturn V. This is the spacecraft that took people to the moon and back. And it was a modular system. When they first started the Apollo program, they didn't have this in mind. When they first started, what they had in mind was more like a Wallace and Gromit spaceship that kind of took off from the Earth, flew to the moon, landed on the moon, took off from the moon and flew back to the Earth. That's a really, really difficult way of doing it because you've got to move the whole thing, the whole craft all of the way. So somebody had the insight to build a modular system instead. So let's just look at some of the coarse-grained modules in this system. So this part of the spacecraft is designed to get the rest of the spacecraft from the Earth into Earth orbit. You can see that's quite a tough job because that's the vast majority of the spacecraft. The top part of the spacecraft was made up of 4 different bits. Here's 2 of them. This is the command module. This was where the astronauts spent most of their time living while they were on the journey. This was designed to get the human beings from Earth orbit back down to Earth again. Primarily, that was the role of this piece, but also it's where they lived. The next bit, this is the service module. This was designed to get the spacecraft from Earth orbit to the moon and back again. That's what this was for. And then there were two other pieces. This is the lunar excursion module, which, again, this was broken down into two pieces. This is the bit that they actually landed on the moon in. So the first bit is this was designed to get the astronauts standing up. There were no chairs. They had no chairs because it reduced weight by taking the chairs out. So they stood up, and it would take off from the moon and get them up into lunar orbit to rendezvous with the other two parts of the spaceship. And then there's the bottom part, which took the lunar excursion module and landed it on the moon. Modular systems give you options. They mean that you can do things like you could farm out the production of these systems to different groups of people. In this case, this part, the lunar excursion module, was built by one organization, and the service module and the command module were built by other companies, completely different. It also means that you can kind of reactively compose the spacecraft into different configurations to solve different problems. So when the spacecraft took off, this part was stacked in the cone bit that was behind the service module and the command module, and then it docked to kind of join this up to take it to the moon. When the Apollo 13 disaster happened and it blew up the service module, they reconfigured the spacecraft to be able to use the lunar ascent module as effectively a lifeboat to save the lives of the astronauts. So it gives you all of these options. It also means that you can start working on stuff that's easier to comprehend. In technical terms, lean processes talk about batch size. They talk about reducing the batch size of things to small pieces. And one of the themes of today's conference, talking about microservices and things like component systems like Docker and Kubernetes, are kind of part of that kind of thinking. So we could decide to write our software in big pieces and deploy it infrequently in the top line. But that's a low-quality solution. It gives us poor feedback. It doesn't allow us to learn very quickly. And each piece is complicated and risky. Or we could decide to break our problem down into small little pieces. Each piece is smaller and simpler and lower risk. It turns out that if you kind of evaluate these different strategies, this is much more efficient and much higher quality as an approach to solving problems. I've used two words in my list of 5 things that are very close together, and particularly in English, they're very similar words. But the ideas are somewhat different, and the best way of describing these ideas is this picture that I've stolen from my friend Jeff Patton's book. If you want being iterative, this is how you work. You kind of do a rough sketch, and then you refine it and refine it and refine it until you get to kind of the finished article at the end. If you're being incremental, this is more about this modular thing. You're going to do a piece, and then another piece, and then another piece, and you join the pieces together. Again, if we think about software engineering on any kind of scale, I can't imagine us being able to do that without both of these techniques. We need to decompose systems into small pieces that we can work on, and we need to apply iterative thinking as well as incremental thinking to kind of manage the evolution of our systems as our understanding and learning of the problem domain and our technology grows. We need to be experimental. An experiment is a procedure carried out to support, refute, or validate a hypothesis. Experiments provide insight into cause and effect by demonstrating what outcome occurs when a particular factor is manipulated. I'm going to tell you another space story to try and illustrate my point. In 1961, John F. Kennedy, the American president, stood up in Congress and said, we're going to send a man to the moon by the end of the decade and bring them back safely. That's what we're going to do. And everybody in NASA went, because they had no clue how to do that. In terms of where this sat in history, Kennedy's standing up in Congress saying we're going to send people to the moon and bring them back safely by the end of the decade, 2 weeks after the first successful American space shot. This first man went into space. The first American in space was a guy called Alan Shepard, and Alan Shepard was a ridiculously brave man. because essentially his space mission was to sit in a tin can on top of an intercontinental ballistic missile. These missiles were blowing up on launch all of the time at this period because they hadn't got all the bugs out of them yet. He sat in this tin can. He was launched 100 miles up and then parachuted in the tin can back down to Earth. That was his space mission. It was minutes. It didn't even go into orbit. 2 weeks later, Kennedy's saying, let's go to the moon. Wow. So all the people in NASA are going, how do we do this? So Kennedy's just kind of painted this vision. He's kind of established this goal. He's said, I'm a politician. I have no idea how to do this. Let's go to the moon. You're engineers. Figure it out. I was giving a version of this talk a couple of years ago, and somebody said, is this the most expensive user story ever? And I think it's a candidate. So he's kind of come up with this picture, this vision of where you want to go. And here are some photographs of things that NASA had no idea how to do at this point. So they hadn't got launches sorted. If you look at a montage of launches from this period in history, it's basically rockets exploding on takeoff. They hadn't done multi-stage vehicles yet. They hadn't got the separation. They hadn't got the splashdown thing sorted. The next mission after Alan Shepard was Gus Grissom, and his space capsule sank and wasn't recovered. Nobody had done a spacewalk. They hadn't got spacesuits yet that you could successfully kind of manipulate and do a job with. So people walking on the moon wouldn't work because the spacesuits they had at the time, essentially they blew up like a balloon and you couldn't move. When the first person did a spacewalk, he nearly died because that happened and he could barely manipulate to get back into the capsule. Nobody docked two spacecraft together yet. Nobody. So mission control wasn't sorted. All of this stuff, they had no clue. So Kennedy stood up in Congress. Where do you start? You know, given this goal, where do you start? So one of the ways in which you start is you hire really smart people. This is Margaret Hamilton, and Margaret was the first person to use the phrase software engineer. Software engineering. She invented that phrase. She was the lead on the flight control systems for the Apollo program. It's her software that saved the mission when Apollo 11 landed and they were getting errors. It was her software load shedding to make sure that they focused on the critical work to safely manage the spacecraft. And so she started applying some engineering thinking to what everybody laughed at her at the time because, you know, it's not engineering, it's just going to plain writing software. It's not real engineering, is it? But she thought that it was, and she started applying some engineering thinking and discipline into the work. But where do you start? When you set a problem on this kind of scale, where do you begin to even think about it? This is a picture of the Earth-Moon system, except it's not. This is a child's storybook picture of the Earth-Moon system. This is a picture of the Earth-Moon system to scale. At this point in history, no human artifact had been more than 1 pixel away from the planet Earth. So problem one, how do you get anything from here all the way over to here, and then back again? So you can kind of imagine the NASA engineers the day after Kennedy stood up having a conversation and saying, "What are we going to do? He's just said that we're going to put people on the moon by the end of the decade. How are we going to do that?" My brother-in-law owns a car dealership. We might be able to get jobs there. No, maybe not. Maybe it's not that drastic. I know. I've got an idea. Why don't we build a spaceship, put 3 astronauts in it, send it to the moon, and see if they come back? And maybe not. The waterfall approach is not what we're going to do here. How are we going to solve this problem then? I've got a better idea. Let's build a spaceship, but an automated spaceship, not put any astronauts in it, send it to the moon and bring it back. And then we'll know how to do that before we put the astronauts in. Well, that's better, but it's still incredibly hard. How can we solve this problem? Oh, I've got a great idea. Why don't we just send a spacecraft to the moon and land it on the moon without bringing it back? That nearly halves the problem. That is a great idea. That's a lot simpler. That's a much easier problem than bringing it all back again. What does landing on the moon mean? Well, it doesn't have to survive the landing on the moon. And that was the job of this mission. This was the Ranger program. This is literally spaceships as bullets fired from the Earth to see if you could hit the moon. That was the job of this program of missions. So how did that go? The first one, remember what I said about the rockets blowing up all the time? Blew up on the pad. The mission of the first one was just to get it into Earth orbit, just to test out the systems. Didn't work. The second one blew up on the pad. Didn't work. If you've ever worked in a big project, the next thing might amuse you in a kind of Schadenfreude kind of way. They hadn't got these things into orbit yet, but they're going to say, well, the next mission was supposed to go to the moon, we'll go to the moon anyway. It took off, it got into orbit, success. They'd learned things from the first two failures. It got into orbit, did the deorbit burn, shot off towards the moon vaguely, but missed entirely. The fourth one, it got into Earth orbit. It did the deorbit burn, fired off towards the moon. The spaceship died completely at that point, but they managed to track it from Earth-based telescopes, and they saw that it actually did hit the moon. So that was kind of a result. The fifth one missed again. The sixth one, it hit, but the cameras failed. So they got telemetry, but no pictures. The seventh one was a success, the eighth one was a success, and the ninth one was a success. So you're NASA in the Cold War. You've got effectively an unlimited budget to solve this problem. How do you do it? How do you go about it? Do you draw a big Gantt chart for the next 9 years? No, that's not how you do it. You kind of have a rough sketch of some thinking about the kinds of things that you might need to do. But essentially, you start trying stuff out. You start experimenting. You start learning. That's what you really do. The Ranger program was all about learning. It was all about discovery and exploration to try and understand the problem in more depth, closer to reality, so that they could get to something that was really useful. This was no use in getting a man to the moon physically, but the information, the learning that they got out of this program was absolutely crucial and fundamental. It wouldn't have worked without this. Being experimental is crucial to solving any hard problems. It's humanity's best problem-solving technique by far. Here's a little example. Have people seen this kind of thing before? The idea is you're supposed to figure out which is the bigger orange dot. Hands up if you think this orange dot is bigger. Hands up if you think this orange dot is bigger. Most of you have seen it before. Hands up if you think they're the same. Okay, so we could try that out. We could experiment. We could evaluate this, and in fact they are the same. It's an optical illusion. Here's another one. Have you seen this one before as well? Okay. So hands up if you think this line is longer. Hands up if you think this line is longer. Hands up if you think they're both the same. I'm sorry, everybody with their hands up now wasn't paying attention. The three people that put their hands up when saying this line is longer were correct because I cheated. It is longer. You can't tell without the experiment. Without measuring, guessing is not enough. We are kind of programmed as a species to guess. And our defense against that is science, the scientific method, and it's about experimenting with ideas. It's about trying things out rather than just assuming that we know the answer. Being empirical, based on concern with or verifiable by observation or experience rather than theory or pure logic. Being empirical is kind of essential. It means that we can start to make decisions based on evidence rather than guesswork. We start measuring things, we can start understanding things. It allows us to distinguish between mythologies and truth. What really matters, what's really valuable, what really works. We can use evidence to make those decisions, data to make those decisions, and we make higher quality decisions as a result. I think it's a reasonable, well, no, I think it's a fundamental truth that we can never be certain of success. One of the ways of thinking about scientific kind of rationalism is it's about an approach of always approaching ideas with doubt. We're going to doubt whether these are correct, and then we're going to evaluate to test them to see whether they're right. So we start off assuming that we're probably wrong. And that's a healthy way of doing things. So we can never be certain of success. We can never be sure that our ideas are the right ideas to go out into production, that our solutions are the right solutions, that they're scalable, that they're bug-free, all of those things. Progress only comes when we risk failure. We are always taking a chance. Whatever we do, however cautious we are, we're still always taking a chance. We can never prove that our software is good. We learn most when reality does not meet our expectations. If we are not experimenting, if we are not taking a chance of being wrong, we're actually not really learning anything new. And remember what I said, in my opinion at least, software development is almost entirely about learning. And so in order to learn, we have to experiment. Production is always going to surprise us. However diligent you are in your automated testing, you can never, ever have enough tests to prove that your software is good. But if one test fails, you know that your software is not good enough, and you can falsify it. You can discard that change if one test fails. That's a different way of thinking, a different way of working, but it's a scientific way of thinking and working. And production should always surprise us. It's an opportunity to go to production frequently and safely and learn and adapt based on what we learn. One way of thinking about this is all of our ideas, all of the software, all of the documentation, all of the tests, all of the data that we've got back from production is really just our best current theory of what the software should be doing and how it works. And we should be looking to kind of improve and refine our theories all of the time to get better and better and better at every step, all of the time. So, fundamentals of an engineering approach. The iterative employs feedback, incremental, experimental, empirical. I think these are also fundamentals of a continuous delivery approach. I'm not hubristic enough to claim that continuous delivery is the only software engineering approach. I'm sure that there are others, but I think that continuous delivery qualifies on my definition as an engineering approach to software development. It's absolutely grounded in working iteratively and in evolving our thinking and refining it continuously. It was built from the ground up on the idea of producing high quality, fast, short cycle feedback. It's about working in small batches and working on modular systems so that we can kind of limit the blast radius of our thinking. We can work on pieces of software that fit inside our heads sensibly. It's experimental. If you think about a deployment pipeline, it's absolutely the perfect platform for carrying out experiments on your software. And it's empirical. We're going to gather information from production. We're going to learn from that, and we're going to feed that back into the start of our chain. It uses these sorts of techniques. I'm rushing ahead because I'm getting close to be running out of time. It uses these kind of feedback mechanisms that provides us this great insight into what's going on in our systems. I think if you're paying any attention, you won't be surprised by this slide. And I'm sure that everybody in this room, you're going to have some kind of technical background, is going to recognize what this is. This is the scientific method. This is a picture of the scientific method. We're going to make an observation. We're going to propose a theory based on what it is that we observe. We're going to make a prediction that follows on from our theory, and then we're going to evaluate that prediction and see whether that prediction meets our expectations. This is humanity's best problem-solving technique. Without any fear of contradiction, this is the thing that has changed us from being basically an agrarian civilization to the modern high-tech civilization that we live in today. So we should be applying this across the board to software development, because software development is one of the more difficult things that we as a species undertake. Mostly that's not how we do it, though. We've learned over the years that you need to do all of these things if you're going to develop software. But we've also learned that you can't do these as discrete steps. These are continua. We need to be doing all of these things all of the time. And we need to establish these cycles, these fast iterations, to be able to learn and adapt and grow our understanding continuously. This is quite a good picture of continuous delivery as it happens as well. This, for example, is what we would call cycle time in continuous delivery. How long does it take you to go from idea to software out in the hands of users? And that's a good measure to drive good behaviors. But also, this is a platform. This is a platform for experimentation. It means that we can have a theory, we can make a prediction, we can carry out an experiment by going out into the marketplace and seeing if our ideas land with our users. Or we can have a different kind of theory and we can make a prediction and we can carry out something in the form of an automated test and evaluate that within the scope of our development cycle. So this gives us this platform for experimentation. So I think that continuous delivery qualifies as an engineering discipline in these terms. One of the pushbacks that occasionally I get is that, yeah, but craftsmanship's a really good thing. And I would agree that that's true. Craftsmanship is about skill, creativity, the freedom to innovate, and apprenticeship schemes, and those sorts of ideas are all kind of software craftsman movement. But by changing one word in this top-level thing, this is just as true of engineering. These things don't detract from craftsmanship. Engineering amplifies craftsmanship. It means that we can apply the innovation and creativity of craftsmanship with greater impact through engineering disciplines. It improves the repeatability, provides guidance and structure when we're stuck, improves quality and efficiency of the process, and it gives us an opportunity to solving problems when we're stuck, when we don't know how to move forwards. We can go back to the scientific method. This is my last slide. So often when we talk about software development, we talk in analogies. We talk about software being like movie making or bridge building or whatever else. I'm not talking like that. I'm not saying, let's be like engineers. I'm saying, let's be engineers. Let's define what engineering means for our discipline, and let's start applying that kind of more rigorous, more disciplined thinking to solving our problems. I hope you have a great day at the conference. Thank you very much indeed for your time.
Thank you very much, Dave, for this great...
But we are constrained by processes that were made for a different era, were made for a different world, a world of certainty.
Be comfortable with the fact that you don't know, no one's going to know everything, and if this is still something that's scary or something that's new, that's okay, and that's normal.
So a mechanic can look at the car and analyse what's wrong with the car. You can look at your code and go, I'm expecting this outcome, and so I can close that gap.
I think it's probably safe to say that open source won the battle of how software is developed.
Und was wir jetzt tun müssen eigentlich, als IT ist, wir müssen es schaffen, nicht unsere eigenen Prozesse zu optimieren, sondern wir müssen die wahrgenommene Geschwindigkeit optimieren.